Okay, well, I wrote clap here, and this is because I would like to thank the organizers for organizing this amazing thing. The food was amazing, but also the talks and everything else was also amazing. So thanks a lot. I think we should clap. I think that's the. All right. Okay, so that took 45 seconds, Steven. Doesn't count. Okay.
Give me an extra minute.
Okay. Okay. Thank you. So, so the question is the following. Well, the question that I'm interested in this talk is how large in our module of finite projective dimension. I'll write PDIM B. So in fact, if you don't want like this title, this could be the title for the rest of the talk. And so let me just set up the usual thing. So RM is a Noetherian local ring, and M is usually a non-zero R module. And if you want, you can make it finite generated. And note what's an annihilator. Well, the annihilator is the set of things in the ring that annihilates the module. Just self-explanatory, and this is containing the maximal ideal member. Okay, so so as far as this question is concerned, we have two very nice answers. And if you're in this, if you work in this area, these theorems are as good as it gets, in some sense. Yeah, I'll send the books once there. So this is the one of the foundational result, and I'll phrase in terms of this question. And basically, this theorem says that if I have a non-zero R module with annihilator as large as possible, namely that the annihilator is everything in the maximal ideal, and yet the projective dimension is finite, then this places a severe restriction on the ring, namely that the ring can have no singularities. The ring has to be regular. Then R is regular. If okay, so why is this true? Let me just quickly make a remark. Well, I mean, having the annihilator as the maximal ideal as the annihilator means that your module is killed by the maximal ideal, of course, by definition. But this is if and only if M is isomorphic to the copies of the residue field. Oh, and K is always going to denote R mod M. And so if this is the annihilator, then this is the residue field, and if the residue field has finite projective dimension, then it's a classical theorem that R is regular, right? Okay, so that's number one. Number two is a generalization of this Osler-Box-Samser theorem, which is called the new intersection theorem. Well, I mean, this is a long history, but it's usually we refer to as Roberts' intersection theorem because he put the final step in the main step in a way, and basically it says that if I have an R module with maybe the annihilator is not the largest possible it could be, but it's still quite large. And I'll write this as if the annihilator contains m to the n, some n, and you should read this condition as having a large annihilator. This condition, and yet the projective dimension is finite. Then surprising that the ring cannot have any worse singularities than being Cohn-Macaulay. Then R is Cohn-Macaulay. So if a ring admits a module, so the lesson from these two fundamental theorems is that if a ring admits a module with large annihilators and yet it's homologically finite, then the ring must have nice singularities.
Is such non-zero M?
Or yeah, yeah.
Like for all non-zero.
Oh, they exist. Yes. Okay, so my goal is again just to make precise this how large can the annihilator be, and turns out that because of this theorem, I can restrict my attention to just Cohn-Macaulay rings. Otherwise, there will be no modules with big annihilators and have finite dimension. So I'll quantify this in some sense to quantify these theorems, and or what it means to have large annihilator. And I'll use this invariant, which is called the Lowy length. And it's the smallest I such that m to the I is 17 right? So for example, if the annihilator is the maximal ideal itself, then the Lowy length is 1. If the annihilator contains m to the n, then the Lowy length is at least finite. Doesn't have to be finite. So, and also here, note that small Lowy length means that smaller power of the ideal is inside the annihilator, means the annihilator is large, right? Means large annihilator. Okay, and to make this title of this section precise, the number that I'm interested in is the following. Namely, I want to consider the smallest Lowy length, which means how big that annihilator can be, where m is non-zero and the projection dimension is finite. So I guess, what is this integer? And there seems to be some kind of it seems to be very tightly related to the singularity, right? So for instance, this number, if R is not regular, this number has to be at least 2, right? Because if it was 1, then by this theorem it would be regular. So if it's not regular, it has to be at least 2. And it turns out that the worse the singularity, the bigger this number is, meaning there's a restriction on how big the annihilator can be. So that's the idea. Any questions so far? Sure. Yeah, it doesn't have to be, but yes, let's just say it's finally generated throughout. No, it does not. Yeah. Also, I guess, let me also note that if I have this condition, this means that the annihilator is M primary, right? It contains the power of a maximal ideal. So these are, in the finite generated case, these are all modules of finite length and finite project dimension, hence the title. Okay, so we have a philosophy in this area. The guiding philosophy, and okay, let me just explain this. So now, by section theorem, I can assume my ring is Cohn-Macaulay local ring, and then note that if consider R modulo this module, this quotient, where is X is a maximum regular sequence. Meaning it's a system of parameters, but it's Cohn-Macaulay, so it's going to be regular. So this means that by definition, some power of the maximal ideal is inside this, because this is a system of parameter, and of course this is the annihilator of this module. So in particular, this is a module of finite length, or I guess by how I'm motivating it, is a module with very large annihilator in our sense. And also the projective dimension is finite. It's D. By the way, D here is the dimension of ring. Well, I mean, why is this true? Well, this is because the Kazul complex is resolves our thing, right? Okay. And okay, so let me just write the guiding philosophy here. So the point is that such quotients by these SOPs are simplest or smallest are modules of finite length, or hence large annihilators and finite project dimension. Then okay. So what do I mean by this? So this is and also it kind of intuitively makes sense, right? I mean, the Kazul complex is the simplest resolution that you could write. At least that's everything else has to be more complicated, or it seems to be more complicated. Okay, so here's just staying on this thing. Here's this guiding philosophy, as I'm mentioning it, is made precise by several conjectures in this area, which is basically all open. But these are the conjectures. assume that R is Cohen-Macaulay and M is a non-zero R module. And let's just make it finite length, which also is if and only if, because I'm assuming everything is finite generated from now on. Sorry, yeah. And the project dimension is finite, meaning the modules that we're interested in. Then, number one is that the Betti number, the ith Betti number of M has to be at least as much as the ith Betti number of R modulo X for some, hence any, right? SOPX. Again, this means, I guess, in terms of if the smallness or bigness is measured by these, how many, syzygies you have at any given stage, that means that the modules of, among all modules, the minimum is achieved by the Koszul complex, right? And this is, of course, the famous Boxone-Eisenberg-Horrocks conjecture. I mean, this is very, very open. Ryan and I sometimes joke whether we'll see this proof of this theorem in our lifetime. I'm not very positive about this one. I think it's, yeah. Okay. The other one is the length of a module is, again, you take the minimum of lengths over all R mod X, for X SOP. And, a module, an arbitrary module of finite project dimension will have at least this minimum, meaning the minimum length amongst all modules of finite length and finite project dimension is, again, achieved by such quotients, meaning that these are, again, the smallest module in the sense of measured by length. And this is the recent conjecture of Eingerma and Walker. So this is also very open. In the local case. So these are really conjectures in a very, very real sense. But these guys proved, this is Eingerma and Walker. So these guys proved it when R is a standard graded localization of a standard graded K algebra, meaning when the ring has some underlying graded structure, a question like this is true. Without this thing, we know for cyclic ideals, true for cyclic ideals for in dimension at most 2. And this is due to this guy named Andrew and myself. Okay. I just wanted to mention that. But actually, so in dimension 2, for non-cyclic modules, the question is still open in mixed characteristics. So it's like somehow it's hard to answer these things. Okay. So finally, the conjecture of interest for us is this is the third one, and this is due to Claudia Polini. H is Hunicky. I forgot who P is. CH. Oh, sorry.
Yeah.
P is for Polini. C is for Corso, Hunicky, Polini, and Bern-Ulrich. So okay. So these are so they just replace the length with the Lowy length. So the Lowy length has to be the minimum Lowy length amongst all modules of finite length and finite project dimension is achieved by a quotient by a system of parameters. Okay. And this is what we're. All right. So this minimum means that how large can the annihilator of a module like this can be, and the conjecture says that any other module of finite project dimension cannot have an annihilator that's larger. It has to be smaller, right? Because if the Lowy length is bigger, then the annihilator is smaller. Okay, so right. So previously, what was known about this thing was this for people Abramov, Bookwise, Eingar, and Miller. This was back in forgot 2000 something. 2000, let's say 2000s. Oh, 2010. Okay, 2010. Okay, 2010. They proved it under this conjecture 3 is true when R is Gorenstein and GUR-MR is Cohn-Macaulay. So in some sense, I think this is a, this is a strong restriction, but nevertheless, it does take care of all the localization of standard graded Gorenstein algebras. Because in that case, the GUR-MR is in fact Cohn-Macaulay. So they proved this, and their technique was something called this index. This uses this invariant code index, and I don't want to get into this, but this is invariant, and somehow this invariant is related to this quantity minimum here, and somehow it gives you, and the proof is not bad at all. I mean, their proof is like a couple of lines. So, any questions so far? Okay. Yeah. Yeah. I mean, so if the yeah, so I mean that's a good question, and let me just. So the question, if I heard it correctly, was that whether is it possible for a Cohn-Macaulay ring to have a non-Cohn-Macaulay associated graded? And in a way, that is the main issue with these problems. Is that if I have R, let's say K, x1 through xn, and let's say we're in the affine case, and it's some ft. If these fi's were homogeneous before that, then the GUR-MR, and let's say this is Cohn-Macaulay, then GUR-MR is also Cohn-Macaulay. But if these fi's are not graded, meaning that these are, we think of it as a local ring and these are not graded, then GUR-MR tends to be not Cohn-Macaulay because you need a lot more generators to cut out the tangent cone. Like these initial forms will also be the ideal defining this ring, but you need a lot more, usually. Yeah. Okay, so no, but that's something I think worth exploring, especially with 2 and 3. Yeah. So for the next 13 minutes or so, I want to theorem with Paulitz. Oh, I don't know why I'm writing this first. Paulitz, this is okay. So now this is finally published in 2025. Yeah. Yeah.
We just had a situation with Jake.
I see. Okay. Okay. So what we proved is that what we proved is that we basically proved this theorem. So the conjecture 3 holds when without any assumption on the GUR-MR is Cohn-Macaulay. So namely that we remove the Gorenstein hypothesis, and in fact, we don't also need, so these theorems require the M to be finely generated. We don't even need here M to be finely generated. So this is the theorem, and in some sense, I think the real nice thing here is the idea that we had, and it's a, well, I mean, I shouldn't say it myself, but I think it's a very nice idea. Hopefully I can, yeah, okay. So this seems to be the, this is what makes this work. Let me just give you like a proof sketch. And then after this, I'll tell you about some of these new ideas that we've had since, which, well, okay, first let me just say it. So what you do is you choose a system of parameters that's sufficiently general, linear system of parameters that's sufficiently general. And the reason for that, which is this move is not so surprising, because it turns out that these minimums are achieved when you choose a sufficiently general linear things, because that's what really minimizes it. We don't quite know it for this one, but at least under this hypothesis, we also proved that if you choose a sufficiently general linear system of parameters, then this is the what that achieves the minimum. Okay. Oh, yeah, let's just make that assume normal M is infinite. So we can reduce the case by doing a Friedman-Platt extension to the case, but yeah. Well, not equal to infinite, is infinite. Okay, so I choose this, and then if I choose sufficiently general, what this implies is that the sequence of initial forms, this was And Caitlin was telling us how this is done in GRM R. Now these will all be degree 1 forms in this associated graded. Is going to be a regular sequence. Because I assume that GRM R is Cohen-Macaulay. Okay, then right. Then the fact that we have a regular sequence after you go to the associated graded allowed us to prove the following thing. And so I won't really talk much about how we prove this, but it has to do with the fact that we look at the linear part and somehow the Koszul complex on the linear part, I take the Koszul complex on this thing, I look at the linear part of the complex, meaning I took the associated graded, I get the Koszul complex on these elements. And the fact that this is a regular sequence means that Koszul complex does not have homology except in degree 0. And somehow that allows us to prove this key lemma. And the key lemma is the following. So I take my residue field K, and I can look at the map from K to this quotient by this thing where I send 1 to a Sockle element, where S is a Sockle element of maximal order. Meaning I pick something that essentially lives in the last spot. If I look at the, I mean, these are not graded, but nevertheless, if I look at the, I mean, this is an Artinian ring, so m to the some power is going to be 0. So I'm looking at this element that lives in the last power. That is, so maximal order, i.e., S is in m to the, let's say, n, but m to the n plus 1 is 0 in modulo xt. Okay. And then let's say this n is what's called order of S. And then you can note that the Lowy length is going to be plus 1, right? Because m to the n times m to the n times this thing is not 0 because this thing survives, but m to the n plus 1 is 0. So that's why this is the Sockle. This is the Lowy length. Okay, so I'm not stated the lemma, but okay, so this is the lemma. So the lemma is I can now look at this map, look at the free resolution, minimal free resolution over R. This thing, Koszul complex, I'll just denote K on this thing, and these are both minimal free resolution, so I have a comparison map between these two things. And the claim is that then the sigma of this F is all in m to the n of K. And let me just draw the picture for this. So let's say I have F0, FD. The resolution of K keeps going, but I have like K0. And here I'm lifting this multiplication by S. So here I have the multiplication by this. KD. This stops here. I have the sigma D. Maybe here I have sigma D minus 1. And this is sigma 0. The point is that the sigma, if I choose bases, right, these are all free modules. If I choose bases, the entries in the matrix, once I choose a basis, are all going to be elements in m to the n power or higher. Yeah, so they all lie in sufficiently deep power of the maximal ideal. So that's the lemma. Okay. Any question about what the lemma says? And this n is this n. This n and this n are the same thing. So in some sense, you should read this lemma as saying that we saw the Lowy length of this quotient in a homological way. Like we could, we saw it in a chain map. Okay, so continuing with this sketch, we now I'll give a key observation. So what's the key? Right. So now let's say M is an R module. So this is continued. M is an R module, and I have a chain map. I can tensor with this, and I have this chain map sigma, and then so I can do sigma tensor RM which gives me a map from M to K tensor M, right? And so now the key observation is the following. If the Lowy length of M is less than N, where N is again the same, this order, right? Then let's see what happens. Well, I have F0, this sigma FD plus 1, FD plus 1, and so on. And I had a map to, I guess I'm repeating the same thing I'm saying. KD and 0 and whatever. And so I'm now tensoring with M. So I get tensor with M, tensor with M, tensor with M, right? And these are sigma 0, tensor with M, and sigma D, tensor with M. Okay, now let's think about what this condition says. Well, this condition says that the annihilator M to the N is inside the annihilator of M, right? So M to the N annihilates the module. But all these sigma i's that are appearing in this thing, because of this key lemma, they all lie in M to the nth power. So these are all zero maps. So this thing is actually under this, when the Lowy length of the module is too small, or equivalently, if the annihilator is too large, this cone, if I take the cone of this thing, this is what you do when you have a chain map. You always take the cone of F tensor M and K tensor M. And when this, am I still under this assumption? If the Lowy length is too small, this is the zero thing, right? If I take the cone of the zero map, this is nothing but a direct sum with a shift. Like this. And here, it's just basic by definition. This is the same thing as I could first take the cone of this map sigma and then tensor with M. Yeah? Okay. And I'm taking a cone of a chain map that was lifting an injective map on the first thing. And so it's a homological exercise to see that this cone of sigma is actually a free resolution of R modulo X comma S. Because if you look at the long exact cone sequence, well, this is a fact. Because the first map is injective, so the H1 of the cone is going to be 0 because it comes as a kernel. But this is a resolution of a module. That's the key point. And so now I can just look at the Tor. I can look at the D plus 1 homology of cone of sigma tensor M. This is D plus 1 homology of K tensor M, but K is only considered of degree 0, so this is just the 0 thing, plus the D plus 1 homology, this. But I have a shift here, right? So if I remove the shift, I have to remove this D. So I have that thing. So this is, as I said, this is a resolution of a module. So this is Tor of D plus 1 of a module R modulo X comma S against M is the same thing as Tor of D of K against M, because F is the resolution of the residue field. Well, if the projective dimension is finite, well, it's a modulo finite length, so this is non-zero, right? But if the projective dimension is finite, then projective dimension is at most dimension of the ring, which is D, right? So this has to be non-zero, but we're getting that this is non-zero. So that's a contradiction, right? Does the contradiction make sense? Yeah. Yeah, so this is non-zero, so hence this implies that this is non-zero.
Any plot has to run up to D plus M has a like that.
Yeah. So if this, so what we're getting is that if I have a module of Lowy length at most n, one could see this as saying that core of d plus 1 of this modulo against some other modulo is non-zero, which means that M couldn't have finite project dimension. I guess I should have just said it like that. So hence, so the conclusion of this little calculation is the following, namely that if I have a module of finite projective dimension and the Loewy length of this module is finite, then the Loewy length had to be at least n plus 1. Because as we clearly saw, if the Loewy length was if it was at most n, then the projective dimension had to be infinite. So there had to be at least this, and somehow this is this thing is the minimum. Well, how do we get this? Well, you just apply with M R modulo some other SOP, and you just do the same calculation, and this again tells you that the Loewy length of R modulo Y of some SOP is bigger than the Loewy length of the general thing I chose. Yeah, so this is the proof. Okay, any questions about the proof? Well, you can take your I forget who's in. Well, you can just take, let's say x1 through x1 is your maximal ideal. Then you just take d many well, these are not the same thing, I guess one. D many linear combinations of these things, and these coefficients that are appearing lie in an open set of the parameter spaces. Okay, so how many? So I don't know, a to the n, because I'm pulling things from I need C1 through Cn coefficients. A to the n, maybe 2d. A to the n d, yeah. Yeah, because I think you have d many coefficients or n many coefficients, n tuples, and you have d many of them. So, and so it lies in some open set, in the Zariski topology. Okay, so yeah.
You know, like explicitly how to describe the unit size there?
No, I don't know. Yeah.
Maximum of the Loewy length of R mod SOP. If I did not start with a sufficiently general SOP,
Yeah.
What's the problem?
So every sufficiently general SOP is going to have the same Loewy length. They all achieve the minimum.
Yeah.
Oh,
This,
then I don't have the lemma. So I don't.
Yeah. What?
So the sufficiently general aspect was that if I have a sufficient general, when I take the initial forms, it needs to be a regular sequence in GRMR. So somehow we're pulling off the information from the GRMR. That's the key thing that this being Cohen-Macaulay allows you to do, and which is why we can't get away from this assumption. It's very annoying, but yeah. Okay. Okay. Let me now talk about newer ideas, and you might think, oh, it's this is a nice trick, or maybe not so nice. Yeah. 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 For instance, if GRMR is Cohen-Macaulay, R is Cohen-Macaulay. But in general, yeah, I mean, it happens, but it happens, but not, I guess it doesn't always happen. I guess that's the. Okay, so yeah, so what I was saying, oh yeah, so you might see this as a nice trick to do this thing, but I think at this point we kind of know what's the truth behind what's really happening here, and I'm not sure. Now this is all some newer ideas. Okay, this is all very tentative. I mean, this is not refereed work. Up until this point, it's correct, but I don't know from this one. Okay. So okay, so let's see. So let me give you the what we did in the proof, and then somehow tell you maybe the right way to think about this thing. So what we did, so we took some special SOP, let's just say. We look at the map on the socle, we lifted the, we lifted to the map to the resolution, and we deduced something about this sigma, right? We said that these entries of this chain map are all in the sufficiently high powers of the maximal ideal, and that was the key point. So, but turns out that actually you don't need the whole sigma. You only need, so the important part is that you only need the sigma d from fd to kd. And kd is, it's the last module in the Kazul complex, which is just R, right? So do I have the picture still? Okay, let me just draw the picture again. So I have this thing, I have this thing, I have this thing. So we thought that this chain map is this whole thing, but instead of this, actually the whole thing, right? Instead of this, turns out that I can just restrict. As far as where does the entries defining this map lie in, it's only important that we look at the last thing. Okay, but sigma d is a map from fd to r. So in the derived category, I can view sigma as a map from f to the d suspension of r, where r is viewed as a complex concentrated in degree 0. Yeah. So sigma is really an element in xd or kr. So instead of viewing this as a chain map, which kind of depended on the choice of the on the SOP, we should really view it as an element, in the deep extension of k against r. And this, in some sense, is a derived socle. But I will not pursue what I mean by this. Okay. And then, okay, what happened? Okay, so next step was that once I had that chain map sigma, it's right here actually, I don't have to even erase. Once I had that chain map sigma, I could take any R module, I could tensor with M and get this chain map. And obviously the standard thing to do once you have a chain map is to take homology. And what we got is that once I take the d homology of this thing, it gave me a map from the d homology of this thing, which is tor d of k against M, to tor d of this Kazul complex, let me just say R x against M. But let me just quickly mention what this is. This is just the set of things in the module that kill the x, right? Because the Kazul complex at the very end, up to signs here, let me just say plus minus. Up to signs, this is what the Kazul complex looks like. I'm looking at the tensor, so I'm looking at the kernel. So it's the set of things in the module that's killed by, or that kill the whole sequence, which of course is a submodule of M, right? So I really have a map. So I was really looking for the map from this to this, right? But this is a k vector space, so this uniquely factors to the socle of M, which is R k against M. It turns out that we're really looking for this map, meaning once you had that sigma, it induces this. In some sense, it's a canonical map from tor d km to the socle of M. Okay. And then, so in this new perspective, in terms of think of an element in the extension, this is really, I have a thing in xd_kr, and this thing in xd_kr is inducing a map from tor d km to R km. And finally, the third step was, if the projector dimension of the module was finite, then this implies that tor d km injects onto R km. And so this is exactly what we used, right? So we took a module of Lewis length at most n, then this map, the map that we got, by looking at the Dth spot, since everything was in the m to the nth power, this map was actually 0. So hence we deduced by using the contrapositive that projective dimension of m was infinite. So, so in the new perspective, what we really have is that I have this sigma, which is an element. It induces a map on this. So the point is to look at the kernel of the toward DKM against Omar KM, where this is induced by the, so look at kernel, and if this is non-zero, then that tells us that the module had infinite projective dimension. Okay. Okay, so now I'm really going to, if at this point you're kind of losing the thread here, it's fine. But now I'm going to, lose the thread more, in a way. Okay, so I'm going to talk about this final twist. So this is a question about modules of finite projective dimension, right? And so let me just give you the spoiler. Turns out that you can ask this question completely in the singularity category of R, meaning singularity category of R is a category where you kind of forget about all modules of finite projective dimension. You just kind of kill them. You make them 0. And somehow this question that really involves these modules can be phrased entirely in the D-singularity category. It means that these questions are really about the singularity of the ring. That's the point. And let me just quickly give you this sketch on what I mean by this. Well, this is what I mean. So I have let's say R is Gorenstein. I don't have to, but let's just assume that it is. Then turns out that I have a map from Omar KM. I have a natural map from this to this. Note that if R is Gorenstein, it's a ring of type 1, so this is really K. So this thing is really toward DKM. So this thing is really the thing that's showing up here. So given an element in the XDKR, I get a map like this. It turns out that the thing that the kernel of this thing is really what's called the stable X of degree -1 of K against M. And the theorem, well, this is not a theorem, it's a proposition, is that the projective dimension of M is finite if and only if the stable X, however, this is defined in the D-singularity category, if that is 0. So what that gives us is that yeah, what does that give us? That gives us the following. I can now make this following conjecture, namely that if a lower length of a module is smaller or strictly smaller than GLL of R, then this negative X group of K against M is non-zero. And this is a question I could phrase in the D-singularity category of R. GLL is this minimum. And the point is that the Lowy length conjecture of this conjecture and the claim, or the point of this proposition is that this is equivalent to this conjecture. Meaning, meaning you can phrase this in the D-singularity category. Well, in words, I think what it means is that, okay, so if the low length being smaller than GLL of R means that the annihilator is too large, right? If the annihilator is too large, then essentially I get non-zero elements in this extension. And so an intuitive way of saying what these non-zero extensions are is that these are elements from a shift of K to M that are unbounded. So if the annihilator is too large, then this module admits these unbounded maps from this shift of K to itself. And, and this is equivalent to the other thing. But, but I think this does not really get into I don't think how it's going to help other than. Yeah. Well, with the shift, so I'd have to put the. Yeah. So yeah, so if we're in Gorenstein case, you could just look at take high enough CZs for both. Look at the stable Hom from the CZs. So, well, I'll just, I don't think how it's going to really help us to really make progress on this problem, other than the fact that this equivalent characterization really tells us that this method that Joss and I had is really the only way to prove this conjecture. Meaning because this injectivity, this map being injective is really equivalent. So in some sense, that is the only way to prove the conjecture. But I think Ben Briggs was here, and I was telling him about this stuff, and he was like, well, you can do all these homological tricks to translate question from one to another, but the fundamental question is, what is so special about going modulo a sufficiently general SOP, and how does the homological algebra really change? And all this does not really help with that. So in some sense, we're avoiding the main thing, and I think that's the real. Yeah, I don't know. This looks just. This bothers me a lot, but this is it. Okay, thanks. Yeah. 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 So okay. So one other thing. So now with this new thing that we've done, I guess this part thought about. One thing that we learned, I think it's kind of related to the question that you're asking, is that. So we chose this sufficiently general thing that was a regular sequence, and we got that this sigma had this right property, right? But actually, what we've now proved is that it didn't matter whether this was sufficiently general or not. When I do this sigma, which is doing which lifts the map that's multiplication by the socle. Where the sigma, maybe like the first d-1 spots, maybe the order is all over the place. We don't know anything. But at the dth spot, it doesn't matter what SOP you chose. It's always going to be of the right order. So somehow the choosing the x1 through xe, but we cannot prove it if we do not have this thing. But somehow it just seems to not matter whether this x1 through xt was a regular sequence in GAR-MR. This lifting property that we need is true regardless. It's just that we can't prove it directly. I mean, indirectly we can, but yeah. Yeah. Yeah.
Or like obstructions to having finite projective function.
Yeah. Oh, cool. Yeah. This is if and only if. Yeah.
Yeah. So if you know, so if you know how big the kernel is, does it tell you about the complexity or curvature of that?
I don't know. I mean, this is like, so if the grammar is Cohn-Macaulay, we're seeing something very rigid, that namely that this kernel is actually just in the entire total KM. But I think we suspect that when you're not in the grammar Cohn-Macaulay, maybe this map is not zero, but nonetheless you get this non-zero. Yeah. Yeah. Yeah.
Like the Ben's overarching question. I don't know what happens in homological algebra for modular sufficiently large.
Yeah.
Sufficient. If you could describe that U over there in the parameter space, Or if you used a different parameter space that wasn't just outline space.
Yeah.
Then if you have a description of that view, does that help you understand the homological algebra?
Yeah, I don't know. Yeah, I don't know. I don't know what would even, yeah, I guess, so, yeah, I don't know. So I don't know how to even phrase that question. So this like, I guess we're trying to see, you have a map from D of R to D of R modulo x1 through xt, right? By tensoring forward, I guess. But there could be other maps too, but there's at least one map. And somehow it's special when this is sufficiently general. So if I know what these are, I don't know. I don't know. Yeah, we need a new idea here. Yeah. Yeah. So when R is Gorenstein, this is the same thing as looking at the MCM, the stable MCM category, where so the objects are just MCM modules. And so in some sense, what you can do is you can pick a module and just take high enough CZ. So that's what it sends objects to. And on the maps, what you just do is you look at Hom of R of, let's say, two modules Mn. You just look at all the R linear maps. Now these are MCM, but it doesn't matter. You can always make the definition. But you mod out by things that factor through a free module. Let me just say what I meant. So meaning I have a map M to N, and if it factors through some free module, then this map is going to be 0. 0. So you look at all maps that do not factor through free modules. So roughly speaking, well, yeah, this is, at least in the MCM category, this is the thing. When it's a hypersurface, that is literally the matrix factorization, the category of R. I guess there it's kind of, we understand, yeah. No. I mean, and this conjecture is open when R is a one-dimensional codimension 2 CI. I mean, we were working on a different approach on this problem, and we thought we had an approach, but turns out that it was wrong. We just found it on Friday. So yeah, it's yeah, outside of the Gorham, Marcon, Macaulay, it's like wide open. Just don't know, yeah.
There, the hard part is the left.
Yeah. Yeah. Yeah.
What is the, can you say what the content of that is?
Oh yeah, it's so let's assume that, yeah, let's assume that R is Gorenstein, and this is actually true. There is something else that goes here. Essentially, you look, okay, whatever. Let's do it for the Gorenstein case. I think that's the key case. So this is the same thing as, let me see if I can do it. QM. Okay, so I can work in the MCM category, so I can replace this with MCMs, the right thing, right? So I have X of, let's see, if I have -1 here, where can I put the thing again? So let's see, so K of sigma 1 of M. This thing, right? If I have the d CZ there, oh, it becomes 1. So actually negative. I can put the CZ here, sorry. I don't know, you can put the one the CZ here, but let me just give you the main idea. Then you can just put the d CZs on both. I mean, just replace it by the same amount of steps. Because yeah, and so this is one of the features of working in the desingularity category. When you replace with high enough MCMs, then it doesn't matter. The comods groups are the same because it's only looking for the eventual behavior of these things. And after this, what you do is you look for this what's called the Oslander-Wrighton duality, which kind of allows you to, oh shit. So d minus 1 of, oh. Yeah. Yeah. Okay, so I don't know what I'm doing, but you can use the Oslander duality with the matrix dual here. But I'm not sure if I'm putting this series is right, but if you just do it, this is going to be the same thing as looking at x0 of the d series of M against K, this thing, right? So we're saying this module is 0. This is an MCM thing, so how do we compute this thing? Well, we kind of look at the what's this complete resolution. Yeah, and if it has no free sum and, you can just assume that's minimal. And so if it harmony and decay, then all these maps are 0. So this 0 implies that this had to be free. Yeah. Yeah, so this is, I mean, this is not a deep, I guess that's the point. I should not really even, it just would kill me if.
Well, thank you.
Thank you.
Announcements.